So, hey guys, uh, I really hope this is visible because the last time I did a recording, as you can see, I actually recorded this whole thing and then just I was recording the wrong video, and so all this just turned out to be waste. Although I would say these are not great notes, I did try explaining a lot of things in this, and the whole recording was over an hour. So I'm gonna try reducing it to close to half an hour because the first chapter at least doesn't need much. So for people without context, I am talking about RL, reinforcement learning, and the first chapter. At least I'm skipping the first chapter. First chapter is intro, which is just explains what RL is. Although I'll go through that concept as well, but in not much detail because it's a very simple concept. And then we'll go to Kiam Bandit, which is like the first problem you encounter in reinforcement learning, and that's actually the simplest problem in reinforcement learning. And then the later chapters build up on the concepts learned from Kiam Bandit. So I'll not go into like insane depth for a lot of things because this is just a very introductory chapter and there's not much to it. And I'll make keep it short, like half an hour. It's not really one of the biggest things, but yeah, it sets the tone for the remaining chapters. So keep that in mind. Okay, so talking about reinforcement learning, simple thing. Reinforcement is could be negative or positive. So negative is you beat up your kid if you get low marks, and you buy him a bicycle or chocolate if he gets good marks, right? So that's how at least the Indian education system works. Used to work, and I don't think it's like that now. So that's general learning nature, and that's what we mimic over here. So we have our agent, and every time it does the right thing, we give it a reward, and it does something that annoys us. We're like, you know what, fuck you. We give it a negative reward. We're like, negative 10 chapters from you. So it has this variable or this value called reward. Also, also you can call it as returns. Okay, and it tries to maximize this value. So its goal, the whole goal of this agent is to maximize its reward. So in a way, it's sort of mimicking human behavior as well, right? So what a reward for you and me could be money. We want to make the most money, so we try maximizing that. So we are an agent in the environment, which is the world, and we're trying to maximize our returns monetary for now. We could also add in family, emotional, passion, career, or growth. All these factors, we could give it a numerical value and also add it into our returns. So we are an agent acting on the world to get some particular reward. Nobody wants negative rewards. Nobody wants to become a what do you say, a prisoner or a bad guy. Hopefully. So yeah. So that's reinforcement learning. Pretty simple. And we get to Kiam Bandit. So Kiam, sorry. So Kiam Bandit. Uh, you know what? Don't look at what's written on the page. Half of this thing, I just wrote it as an explanation. So you can I'll just erase it off or I'll skip through it. But this is actually a good drawing. That's why I'm just reusing whatever I've written. Uh, so yeah, so KM Bandit is the simplest RL problem out there. Okay, and there are a few learning outcomes of this chapter, which I think is a good idea if I write it at the end, like as a summary. Okay, and KM Bandit sets the tone for the remaining chapters. So what is KM Bandit? Okay, you see there's something called number of levers, and I put six, and there's six levers here. Something looks like a slot machine, right? Uh, it is a pretty guessable idea that this is nothing but you have k number of arms, and every time you pull one arm, you get a particular reward of plus 10 or minus 5 or some value. Okay, this could be any value, and this is the game. The game is simply a very random game where you pull a lever and you get some particular reward. Alright, so now the agent is you. Okay, the agent here is you. I'm not writing every single thing. uh, so in for a Kiam bandit case, I'll make the flow diagram somewhere on the right. 1 second. Okay, cool. So here the agent is you for now. At least you always put yourself in the place of the agent and you think about the problem. And the actions here are any of the levers. It could be one, two, three. By any of the levers, I mean you pull one lever at a time, right? So your action could be any one of these levers. So you have 1, 2, 3 till k. For the example that I drew there, k is 6, but k could be any number. And your environment is the slot machine type of thingy. Okay, that's your environment. And this thing is giving you a reward, right? It's displaying this reward. So that is the information you get out of the environment. Is that called, oh wait, action? Reward only, right? Yeah. So the information you get out of the environment is a reward. Reward is a numerical signal which you get out of the environment. As simple as that. So you're getting your rewards. Okay. So this is the, and your rewards are what? Plus 10. Here in this case your reward is your score. And the agent's goal is to get the highest score possible. Okay, get the highest possible score. Okay, it seems to be fair enough, right? So this is the system right now, and you have slot machine, you have these actions, and you have some reward. The thing for each action is the reward is not constant. Suppose so what I mean by that is, if you're familiar with probability distributions, even if you're not, it's a simple understanding. Suppose I'm pulling lever 1 and I'm supposed to draw, uh, just let this be n being the number of times, uh, no actually you know what, uh, that doesn't make sense. Okay, fine, yeah, that's not n, just leave this, sorry. So this is for action number 1. Okay, let's get this right. And then reward frequency, which kind of, you know what, I'll leave it as reward frequency here. Okay, reward frequency. This is your reward frequency. And here you have the rewards being -10, -5, 0, 1, 10. Sorry, that's 5 and that's a 10. Okay, and suppose the reward frequency, I'm taking action 1 forever. Okay, I've taken action 1 for a long time, and I see that it has a very low frequency of 10. Like the cumulative frequency of -10 is like very low, and same case for -5. But there are quite a few zeros and a lot of 5s, and again quite a few number of 10s. Okay, this is what it looked like. I pulled action 1, like I pulled the lever 1 for quite some time, and I got something that looked like this. Okay, okay, fair enough. So who are familiar with the probability distribution, I was trying to draw a normal distribution, or I was trying to draw any distribution which says, you know what, if I pull this long enough, I uh, I average around a reward of 5. If I pull it long enough, uh, suppose n tends to infinity, my total return I'll add new words along the way itself. So return and reward, although they sound same, they're not the same. Return is just summation of all your rewards. This will tend to uh, 5 times n as n tends to infinity, somewhere around this. That's the logic of it. So now what I've tried doing here is I'll take action 1 forever and get this sort of a distribution or this value chart where I understand which value is occurring the most, which value is the most probable as I take action 1. So the goal is to converge to this value 5, okay, quickly, and do the same for 2, 3, 4, 5 till k. And so converge to the averages of all these uh, levers. So in the textbook, there is a condition that initial condition. I don't know if it's mentioned. I don't know if this is a known condition for the agent, but at least as a from an agent designer point of view, you have been given the information that the reward distribution is normal. Okay, is normal for each action. So this is a known information that essentially means if I have to make this drawing better, and if I can make an assumption like I'm not making an assumption. I've been given the condition that it's a normal distribution. So then it looks somewhat like, suppose this 5, it looks somewhat like this. So where my mean and stuff will come here, and this is what my approximation average reward will be, right? So essentially this, and for every action it will be different. So possibly for another action, say action 2, where the average is somewhat here, right? Uh, so normal distribution looks somewhat like this. Good. So yeah, so the peak of this will vary with the variance of it. Okay, so suppose action number 3 has very less variance and a plus 10 reward, so it will look somewhat like this. Terrible drawing, I'm so sorry, but uh, it's not bad. It's alright. So you get what I'm trying to say. Like, as variance increases, its sharpness increases, and then it's more closer to plus 10. But in the question, they've already, at least in the initial conditions, I think in the textbook, they have mentioned that the variance is also constant, same for each action value, at least each action. So it should not really matter. Even if the variance is different, it doesn't really matter, as you see. Okay. So this is the reward distributions for each action, and I think it must be pretty obvious for now that a rational agent's decision making will be like the most rational thing to be done over here is take action 1 some n number of times until some condition where you feel okay, you know what, my average isn't changing much and I feel I've converged to my actual average. So if I keep on taking, I'll probably end up getting my average times n. So that means I've converged to my average, and then even if I change, this average value is not really going to change. I think I confused you more, but I explain it as I keep going. So same thing. So once I feel I've converged to the average value of average reward I get from taking action 1, which we assumed as plus 5 as a hypothetical value. Once I feel that I've converged to it, then I'll take action number 2, then I'll take it n times and then do it until I feel like I've converged to it, and then keep on doing this. Okay, and convergence is guaranteed because at least they've made sure that the reward distributions are normal, and it will definitely converge to a mean. It's not like a random value generator, right? And even if it's random value, okay, it's not random. If it's random, it's a whole other game. If it's random, this is uh, this is just a no, how to say, tidbit or thing. If your environment is random, your most rational decision making is to be random. That's the best way you can play an environment. So this is always this is huge. Fuck, what am I even saying? So RL is always this transaction between agent and environment. So you play your environment, right? And for that you need to understand your environment. That's what we are doing. So in this averages part, you're trying to understand what your environment is, what the probability distribution looks like, what its mean looks like. That's what. So now when I'm taking all these like n samples from action 1 and n samples from action 2, trying to converge for all the k actions possible, what I'm essentially trying to do is get enough information about my environment to then exploit that information. Like once I know the averages of every single thing, I'll just take the one with the highest average and take it forever, right? That's my best bet. So that's what we're trying to do. So there's always in RL, your first stage is always called exploration. Okay, you explore your environment, you try figuring out your environment, you try understanding what it really is, and then your second stage is exploitation. So you'll see this every single place, like everywhere they talk about this trade-off between exploration and exploitation. Because say now after n tries, I feel that action 1 converged to its average value, but it really didn't, right? No example, it's 10 tries. Let the value of n be 10. That means I take action value 10 times, I get a mean, a particular mean, sample mean for that 10 tries, right? So I could be satisfied and tell myself that you know what, this is good enough, and this might actually be the real mean reward I get by taking action 1. I could be satisfied and I could use that premature value and exploit it. I could do that 10 tries for 1, 10 tries for 2, 10 tries for 3 until k, and then exploit it based on that value, right? But the law of large numbers says, although this large numbers, okay, this my professor pulled this out of his ass. No, sorry, fuck, what am I saying? This is an actual thing. Why did Okay, so my professor pulled out this theorem in the middle of the class asking, do you know what law of large numbers is? And nobody raised their hand. And once we heard what the fucking law was, we were like, that's such common sense. Why does it have a law? And until I checked out the proof for it, yeah, the proof is insane. Like, I don't know, I didn't understand the proof at all. I'm very stupid. So the law of large numbers is a very simple thing. It just says if you take enough values of I, okay, enough I, then if I is big enough, your whole summation of xi by uh, I, this makes sense, no? You're like adding 1 for every I till n, so this would be your total number of samples, and this will be your whole sum of the values you've got. So this will definitely converge to your mean of x. This is law of large numbers simply put. Essentially, 10 is not a large enough number for you to be convinced that it has converged to its real mean. That's what I'm trying to get at. So you need a really big n value. But how big should this n be? Because theoretically n should be infinity for you to be completely sure that it's e of x. But obviously we can't keep taking, we don't have enough space and time to take infinite actions. So we need to have a point where we're like, okay, I'm happy with this, I'll move on and then I'll exploit. Cool. I think I deviated quite a bit. But what I was trying to explain was, again, is it 10 times I should choose an action, 100 times, 1000 times, 10,000 times? How would I know? And that is the exploration part. So again, getting back at exploration exploitation, I could explore it by taking 10 actions at a time, 100 actions at a time, maybe close to infinity as well, if I want to be thorough that my means are very close. But it doesn't make sense to take infinite number of times or take 10 number of times. It's somewhere in the middle. It's somewhere in the middle, because taking in at least a theoretical infinite number of times, there will be a point after which my mean value, at least the sample mean, gets very close to the population mean, which is e of x, with very little deviation. This should be like very small compared to 0. There will be deviation, but it's really tiny and you could probably ignore it. So there is a point where n is less than infinity greater than 1, where this thing is satisfied, where it's very, very. Is it less than 0? No, sorry. Less than 1. Less than 0 makes no sense. Yeah. Less than 1. Okay? Well, I just mean it's a tiny value. Alright? So, okay, step 1, find this n. Step 2, once you get it, choose the best action which gives you uh, the highest average reward, right? So in mathematical terms, that sort of looks like this: arg max, which means choose the argument which maximizes, and the argument being action. You have to write it below this: argument being action, argument which maximizes the value of returns. Okay, this is technically what it is. Returns I've defined earlier. It is the summation of all your rewards. So this is your whole reinforcement learning. Choose an action which maximizes your returns. But now our returns after our exploration uh, converges kind of to the average reward you expect out of A, right? So I'm going to write that as R bar of A. So this is the average reward you expect out of A. So choose an action A which gives you the highest average expected reward out of A. Alright. So now for me, A is as valuable as this R bar. Right. So I'm saying if R bar of 1, that is the average reward I'm getting out of 1, is higher than the average reward I'm getting out of 2, then I would say, you know what, man? I like 1 more than 2. I like 1 more than 2. Or you could also say I value, right? I think it works both ways. I value 1 more than 2. So now there is this thing called as action value, which is represented with a Q. Q. Inside you have this action, and then so now essentially whatever I wrote R bar of A, my action value, how good is my action 1, is same as this. It's just different representation. It's again Q of 1 will again be my whole average mean of taking action 1 forever. Alright, so now we're finding this action value named variable for each action. Cool. We are finding this Q of 1, and our action value for now is just like the sum of all rewards by n however times you took for action A, given you've taken action A only, A being action 1 for whatever I've written on the board. Alright, so okay, I'll come back to the whole exploitation thing. So now in exploration, your goal is to find Q values of each action. This is your goal. And then in the exploitation part, you choose to take an action as a function of your Q value. Wait, don't get scared. That's simply saying action could be whatever maximizes argmax, whatever maximizes Q. It could also be some other things. We'll look into that later. But do realize that this is just a function, right? This is just a function of Q. So it's, I could want to take this action every single time. I could want to do something else. I could want to explore more instead of exploit more, right? So we look into that. So first step, find Q values of each action. So now that this setup is made and you guys understand what Q value is and where we're trying to find it, I'll sort of just run through the possible algorithms. I've actually written so much shit. Yeah, so okay, I'll even go through this. I'll probably try using this if I can. So okay, just remember whatever we did till here. Cool. You have Q value. You only have Q value. We haven't done shit. Okay, we have only Q value. Q value for now is the average expected reward. You could, oh yeah, that is literally the definition of Q value, by the way. If you look at the textbook, it is the average expected reward you would get by choosing action A uh, every single time. It's something on those lines. Cool, that's action value. Um, so yes, I think that's what I was trying to do here. I was like, oh, take n action one. If your average is 10, after n tries, you get 10 and shit like that. And goal is to maximize possible reward, possible being expected, given obtained. You're trying to find all this action. Yeah, so this is the notation, returns, conclusion. Yeah, I actually spent a lot of time on this. Yeah, and also see, so you see your return, as I told, is your summation of rewards, right? So as you keep summing them, uh, that's actually wrong. This should be average return. Average? No, actually it should be average reward, not even return. Because return is summation of rewards. And as I keep doing, time step is each time you pull something, that's one time step. Okay, it's like one episode type thing. Cool. So as the time steps increase and I'm pulling reverse, my reward will always keep increasing. It will not really converge. The summation of rewards. Because summation of anything diverges to infinity unless it's like some 1 by n or some shit like that. Right? Or something. You get what I mean. So it should be the average reward, which is what our expectation of R is. And that's what we're trying to find. Okay. I did a lot of unnecessary stuff. Yeah, see, I spent so much time just explaining that it's Q is the average. Again, this is the same thing. Take all your rewards, sum them up, total number of times you have taken it. That is your average expected reward that you could expect by choosing action A. And I got into the algorithms now. Greedy action selection. Okay. Greedy action selection. UCB. Action value initialization. Learning. Okay. Fine. I did that 2-minute deviation so that I get a structure of how much is remaining and what I should do. Because I feel like get stuck in these fundamentals so much that I don't move on to the chapters. 1 second. Yeah. Yeah, sorry, one annoying person is calling. I'll just take this call and come back. 2 minutes. Yeah, fuck. Half an hour's already over. Okay, let's get on with it. This is actually the simple part. If you understood the Q value thing, that is the main thing. The other stuff which I'm going to explain now is just an extension of how you use it. Okay? Keep the exploitation thing in mind because I'll try explaining everything in that sort of a sense. So now, okay, I'll just start with greedy action selection. Action selection. Take a second to think what this could be and just read the name out again. Alright? Cool? Sounds familiar and sounds simple, so don't complicate it. Greedy action selection is nothing but what the fuck I wrote here. That is greedy action selection. We already did this. So is the exploitation part, where choose an value of A which maximizes your Q. I'm greedy, I want more Q. Choose action which maximizes Q. And Q is what? Q is not something special. Q is, if I take action A, how many chocolates on average will I get? Right? How many kisses will I get on average? How many people am I making them happy? How many people are getting educated? How much money am I making? It's on average. It's like yeah, I think. Do I complicate stuff? If I complicate stuff, just put in a message. Okay? It's fine. So it's simply that. There's really nothing in it. So I'm not spending more time on that. Now I go to Epsilon, greedy. That's my Epsilon, by the way. Greedy, action, selection. Okay. Now again, take a second. Look at the one previous to this. Look at this. What could be the difference? Alright. Okay. Noticeably, the epsilon is different. So unlike this, I'm not greedy all the time. I'm greedy some epsilon time. Epsilon being a probability. This is something I keep forgetting. So I'll just make a reference here. Because even here I refer to the thing. Okay. So epsilon is random. And 1 minus epsilon is greedy. Alright. Not a problem. Cool. Okay. Epsilon greedy action selection. Which simply means, simplest shit ever, be greedy, which is choose an action which maximizes your Q. But when choose this with a probability of 1 minus epsilon, and choose a random action with a probability of epsilon. Okay, so if epsilon is 0.2, then out of 100 tries, 80 times you're choosing greedy action, and then the remaining 20 times you're choosing something random. Now why would you want to add this random thing? As I told earlier, there's an exploration factor as well. Okay, you need to keep exploring multiple actions so that over infinity you've chosen all actions enough number of times for you to be sure that this Q value actually converts to their actual mean. Alright, so now, okay, so 100 tries, 80 greedy, 20 not, random, right? So in this 20 random, that means I'm taking the other actions, which are not greedy. So as this value of 100 increases, as it keeps tending to infinity, you do realize this also tends to infinity. And as this tends to infinity, we learned that all your average rewards, will converge to the true average rewards. My mathematical notation is fuck all, but it's simple to understand. T of alpha is true. Whatever I speak, that's what I write. So notation is fuck all, but just like listen to whatever I'm telling. That should be good enough. Cool. So as you do take an infinite number of times, it does converge to your real reward, true reward, and which is what we want. And once it converges to true reward, our greedy action makes more sense. Initially it's not converged to the real reward, right? So your greedy action is really not your best action. You're really wasting your chances. But over a span of infinity, this will converge to the real values, and your greedy action makes more and more sense. You're doing the best action possible. So for that reason, this is a much better strategy than being greedy from the very beginning, because in greedy action selection you're completely skipping step number 1, which is exploration. Okay, you're completely skipping this and you're directly shooting down to exploitation. So as I told, you need to know your environment to really exploitation. Yeah, so you need to understand your environment before you can exploit it, and that's not happening in greedy at all. Whereas in epsilon greedy, You are getting to know your environment. At the same time, you're exploiting whatever you know about the environment. And over the limit of infinity, you know enough to get the best out of your environment. That's the whole ideology of Epsilon greedy. But you do realize the issue with this. Once your exploration part is complete, a limit of infinity, and your exploitation part starts, your exploitation part is actually going on along with your exploration, right? In Epsilon greedy. It's not like two steps. It's going on simultaneously. And that is the issue. Exploitation. Spelling. Exploitation. So that's the issue. So you're exploring, and suppose say your exploration is done. There's a point where exploration is done, and you're like, you know what, man? I can't find other better action other than action number 3, and I would like to choose action number 3 all the time. But Epsilon greedy action selection doesn't allow you to do that, and you're still choosing non-optimal actions at a limit of infinity. For that reason, this performance is not the best, but it is something. It is a step in the right direction. Alright. So I also give a new concept which is called uh, initial action value. Yeah, I'm getting lazier and lazier. Initialization. You know what? Fuck you guys. Initial action. Initial action value initialization. Actually, sorry. I'll do this. Okay. Q initial action value. Q initialization. Okay. Q not. Initial is always not, right? You put, yeah, if you're familiar, you put not first thing. Q not initialization. Initialization for each action. So Q not A. Okay. Suppose before playing the game, I give you some value saying, you know what, man? Actually, no. This one it's a good concept. I think I'll not spoon feed it. If you really catch it on your own, that's a pretty good thing. So I'll give a drawing. Fine. This I think the diagram's there in the textbook, so you should really be able to find this on your own. So these are all the actions. I'm drawing 4 right now, and these are the rewards you get. And I'll draw the true reward with a different color. Okay, I'll draw the true rewards like this. Cool. Yeah, 4 looks like to be the best action. Okay. Okay. So now till now, what did we do? We assume this Q of A to be 0. Q naught of A to be 0 because our Q of A was just the averages, right? If I never took action number 2 and I never got any rewards, my summation of rewards are 0. So my action value of 2 was 0 till now. Till now, that's what we did. So till now, at time step 0, our rewards were 0 like this. Then as we kept taking actions like this over, we got different rewards and like different spectrums. Uh, like suppose it looked more like this, like more concentrated here. Then we saw this shift up, this shift lower because it's evenly spread out, this probably again lower because it's a bit sparse. Okay, you're understanding? So this slowly shifted like this towards whatever its original true values were. As you pick up values, it gets your, this is your Q, this is your Q. It slowly shifted to the true value. This is what happened till now. Alright. Fuck, that's a lot of undos. Okay. And you choose all these actions in a very randomized. Oh fuck. I can't. Okay. Fuck you. It's alright. Deal with it. Choose another color. Pink, I guess. Fuck this. Yeah. So now here you choose the actions. You chose the actions randomly and then they converged and shit like that, right? But say I start. No. I'll not explain it in a spoon feeding way. I'll just tell what it is, then it makes sense, then you'll understand. Cool. So initial value initialization is I'm giving all these some initial value of R, which should be higher than all their true values. This is the condition. You will see why. If I know that I'm not getting a reward more than 10, 10 is like the maximum reward possible on this game, then I will initialize all action values at probably 11, and then I start taking the actions. So now what happens now is, in this initialization, my initial action values are high, and now if I use a greedy policy that performs way better than an epsilon greedy action selection, because of this. I told you epsilon greedy action selection does random actions even at infinity, right? Which fucks it up. But suppose I do greedy and my exploration part is covered by this initialization, and over infinity I'm only doing the like the best action, then I'll make the most reward. And that's what this initial action value initialization does. It's a really interesting thing. So what happens is, so now the true values are always below, right? So suppose I do action 1, because the true value is here, after some time, or maybe immediately after the first action as well. Okay, it could be anywhere between immediately first action or after some time. I'm definitely sure this pink value, at least my expectation of my Q value of 1 is definitely going to dip, because the true value is lower. It's definitely going to dip. And once this happens, now remember, I'm using argmax A of Q. Initially, the Q values are all equal. So therefore, this is just a random action, and I chose 1, and 1 definitely will fall. There will be a point where 1's Q value is definitely lesser than the other Q values. And once this happens, I'm going to start doing 2. And 2 is also definitely going to fall. So is 3. So is 4. And they're all definitely going to fall until only the highest action value remains here and the others fall below it. Like, see, the action values are not going to converge, by the way. Like, unlike epsilon greedy, where convergence is guaranteed, here convergence for all action values are not guaranteed. But you do find your optimal action, because after one point, 3 is going to be here, 2 is going to be say here, 1 is going to be say here. Okay, alright. But 4 is here, and I'm going to keep taking 4. And 4 is never going to go below its true value. Like, it is going to go below its true value, but by the time it would have converged to its true value. So therefore, I have converged to the optimal action, and I am greedy as fuck. So this performs insanely better, given you know that there is one value, like not one value, there are values of R which are definitely higher than all their true rewards or true action values. If you know that information, you can use this strat, and this is insanely better compared to the epsilon greedy, which we discussed earlier. So this is the optimal initialization. It's called optimal initialization because you're being optimistic about each action initially, that each action is good, but then later you learn, oh, everything is shit, and you know what, action 4 is not letting me down the most. Action 1 is letting me down like crazy, 2 is nuts, 3 is also bad, but 4, you know what, manageable, I'll keep doing 4. That is the thought process of the agent in this. So the last one, UCB, very elegant. You know what, I'll just write it down. So your action is, fuck, yeah, no, I know this, don't worry, I got this. Fuck, no, I don't got this. And max A which maximizes, shit, no, I don't got it. See, the thing is, you really don't use this multiple times, but this is just like, you use concepts of this. You don't use this directly. You use like versions of this later in planning. In planning, there's this DynaQ thing, DynaQ plus, in which you add this similar thing. Okay, so now I highlighted this. This is what your UCB is. Now, till now, our Qs were average of returns. Oh, actually, I made good notes. Till now, your Q was your average of returns, but now I'm adding this extra beautiful term over here. Alright, now what does this term do? On the numerator, it has a total number of time steps. On the denominator, is number of times I selected action A. It makes sense. So as time steps increases, your bonus, we call this the bonus component, because that's what it is. I'm adding a bonus based on how many times I've selected it and how many total time steps have passed. Alright? So as my time steps increase, action value of each action is increasing, and the number of times I selected action A, if it's been a long time since I selected action A, and suppose this value is really low, then also the bonus increases. So you understand, it inversely depends on the number of times you selected it. That is, if you selected an action less number of times, then you would want to, it has a higher action value, it has a higher importance. If like I'm playing with 4 levers, okay, I kept pulling 1 2 3, I've not pulled 4 for a long time, and I'm like, I get curiouser and curiouser to what action 4 could be. I'm like, in my head, action 4 has a lot of potential because I've not taken it for a long time. There's more to learn from action A than I could learn from 1 2 3, because I've been choosing 1 2 3 for most of the time. So this, that component of curiosity is somehow added in through this bonus component. That's what I try to add. So that's the simple thing, and that's the game changer. So your action selection is still this. Your action selection is still greedy, but your Q value is not the same. Your Q value is your initial average rewards by n selections. Initial whatever Q of A shit we did earlier is the same thing, but now I'm adding a whole bonus component where this is ln n nt of A. No, it's lnt. lnt. Alright, so total time steps, number of times I selected A. Now you might be wondering what the fuck the C is. The C is anything you want to be. The C could be anything, but obviously there might be some optimal value according to your problem statement, which you need to figure out, but that's a different thing. But C could be anything. It's just any constant. Doesn't really matter. So you take this, put into this, find A, which maximizes it, you're good. And over the limit of infinity, this bonus component over infinity, as we saw, epsilon is trash, and action value initialization, action value initialization is good if you do it the right way. Okay, because just think of the opposite thing, right? So instead of having higher than all true values, suppose I put all the average words here, okay, then and say and a selection action 3, and action 3 is definitely going to go up, and because I'm greedy, I'll keep choosing action 3 forever. So that's trash. So you do understand that. Yeah, think of the other examples, it'll make sense. I think this made sense. So if you do it rightly, this is really good. If you do it wrong, this could be, that'll end up in the worst results ever. But this one, over a limit of infinity, it would have chosen every single action properly, and this value becomes teeny tiny. Okay, very small compared to 1 and approximately 0. It becomes teeny tiny. You could take light, but that doesn't say that you're choosing the optimal action forever. There will be a point where it shifts, but that shifting shifts from optimal action to non-optimal, but it'll immediately jump back to the optimal action once that happens. So it's not like you have converged, so you do some stupid action at some point, but that's way lesser than what you do in epsilon greedy. Cool. And I think that's what I've covered the second chapter quite a bit. We have done these things. Cool. There's nothing much, but yeah, okay, there's one thing which I've not done, which I would suggest you guys sort of do out of interest. I think there's a gradient descent algorithm somewhere. I think policy gradient descent, I think that's what they discuss. I don't have the textbook with me right now, and if I open the textbook my recording will stop. Policy gradient descent thingy, and check it out, because the textbook is descent. You know what, fuck it, anything's fun. So check out the textbook, it's pretty fun. So check this out. It doesn't really add crazily to the chapter, but it is an interesting concept. Okay, it's an interesting concept. Check it out. I will read it. I've not read it. That's the reason I'm not explained. But I am familiar with gradient descent and policy is, but I don't know how they add up together. Okay. Yeah, this policy and all will come in the future. Huh? It's pretty simple only. It's all simple shit, bro. Like, just read on your own, you get it off. Cool. I'm ending it at exactly 50 minutes. Bye.